this video, we are going to be calculating the triple integral of the divergence of the vector field over the volume of the cylinder. That's the first part. But we will be proving the divergence theorem of the given vector field and the cylindrical surface, z equals 0, z equals 2, and r equals 1. Now, I went ahead and did a slice vector plot in Mathematica. You will be starting here. If you notice, this is z equals 0, where I kind of made this plane z equals 0. We will be dealing with the bottom cap down here, in fact, when we do our boundaries. Also, when we do the flux to prove this. So again, we're first going to calculate the triple integral of the divergence of the vector field over the volume of the cylinder. You can think of this like heat flow, like you just heated a burrito, and the instant you took it out, that's when the field started across your surface, not surface, but the volume of the entire cylinder. I'll explain that in a moment. And then by calculating the three flux integrals across the surface of the cylinder, because there are in fact three sides, that's going to be enough to prove the divergence theorem, which all we're going to do is consider every single surface that encompasses our surface, that closes it off, which is actually one of your conditions. So having said what we're going to do here to prove this, let's move on. You are given the vector field x, y, i, y, z, j, and x, z, k across the cylinder, radius 1, of course, respectfully. Now, as I promised here, the divergence of a vector field essentially represents the net flux. I like to think of it in the easiest way you can that you deal with on a daily basis, like maybe heat emanating from a burrito, or if you're a welder, maybe you heated up a metal rod and that's what you would be doing. You would be measuring that. But more so, if that was like a steady heat flow. I won't get into the engineering on how that occurs, but just think of it like you took a burrito out, and within a finite amount of time, we're going to be calculating that net flux throughout the entire 3D region. So this calculates the total outward flow of a vector field through the entire surface of that region, essentially summing up the source or the sink behavior. That is your vector field, by the way. You can think of it like an infinite amount of little vectors, and how they behave from 0 to 2, or 0 to 1, and of course throughout 0 to 2 pi. You're going to sum up all those little vectors, right, throughout the entire volume in a triple integral, which is the core concept of the divergence theorem. You're probably asking yourself, if you're a physics major or anything like this, or chemist, whatever your major is, like, why don't we just do divergence on everything then? Well, that's because perhaps maybe you just wanted two pieces of the surface in physics, right? Or maybe it's just a lot easier to use divergence. Or maybe it's more convenient to use the flux integration. So the useful thing about that divergence theorem is we can go either way depending on the math we've been given. And that's solely what it depends on. Like, how do you want to calculate this, and how difficult is your integrations? Whether or not, that's going to determine which parts of the calculation you're going to be using, whether you're just going to do flux or divergence. So I spent a lot of time on this. Let's move on. Logically then, it would only make sense, right, restating this a little bit better, that you could prove this by constructing a flux integral across each surface that encompasses the volume in question. More so, you do want a closed surface, right? I did mention earlier, maybe you just wanted to do a flux of, maybe you've had earlier on when you were just doing flux, maybe just one surface that you're considering, but here you are considering the entire surface in this problem. That means we're going to require three flux integrals for the cylinder, of course, the top cap, the lateral, and the bottom of the cylinder. So let's start this out. We're going to start with the divergence theorem. And for the purposes of the calculations, I'm going to simply just be setting these up and explaining how we set up our triple integral, like any other logical situation when you're proving it, because the calculations would just take so long. I will do separate videos when I do them by hand. I will be utilizing Mathematica. You can pause it. I won't say pause the video. It would get redundant, so you can just pause it in your own time and look at the program that I've kind of generated myself in Mathematica, respectfully. And you could use that Mathematica if you're good with that. But let's continue. So we're given this vector field x, y, y, z, x, z across the radius 1. Let's first do our del operator. Again, for those each little pieces, right? It's going to give us what we need to integrate down here, right, which you can write del F, right? That's what we're doing here. So we're going to go ahead and we're going to make that connection here. Let's do the calculations. So the derivative with respect to x of your ith component here, that's going to be, of course, y. So let's go ahead and put xy. Let's put it all in, and then your jth component, yz, and this del operator is acting directly on the vector field, respectively, as written. When we do this, the derivative with respect to x is y, and with respect to y of the kth is z, and with respect to xc is x. So this gives us our del f vector form here. We're going to go ahead and put that in our integration below. Okay, so again, your del f is that down there. So what's going to be y? Now I'm going to write, you can write this in any order. We're not in vector form anymore when you take the gradient of this, so let's just do x plus y plus z. It's a little easier on the eyes. And you could do this with Cartesian, but I went ahead and I switched this parametrically. Now, if you're dealing with Flux, that's going to change up, and I'll show you how to deal with that. But if you're just doing divergence, we are using cylindric coordinates. So x is r cosine theta, y is r sine theta, and z equals z. And if it's a cylinder, it's 0 to 2 pi. We're considering the closed surface, and 0 to 1 for r, because it's a radius of 1, and 0 to 2 for z as given in the problem. So this is your setup. So 0 to 2 pi for your theta, 0 to 1 for r, and 0 to 2 for z. And it's a straightforward calculation. This gets us our triple integral setup for what it is that we're dealing with. If you wanted to see that in polar form, I went ahead and included that. Your dy dx, of course, is r d theta. I always like to break it up so I know what's going on a little better, just as if I was doing stoichiometry and chemistry. Cringe. But hey, you know, you know, as a metaphor, I know that I'm doing this the right way when I do it as such. And of course, we're going to be using cylindrical. That's going to be dz r d theta. Your x is, of course, going to be r cosine theta. By convention, r is changing, and so is theta. And z is just a, in this case, z equals z. So let's go ahead and do this. We then put in our components, and I switched it up. So apologies for that, but I don't want to go and change that. But your y, z, and x, it doesn't matter the order. Just put them in there. Do not forget your r, right? You might be setting these up right, and then you get the integration wrong because you forgot your little differential area element here that I have, and for that reason boxed here to kind of show that. Now let's use Mathematica. It seems that we're not going to be able to do the flux integrals as a time constraint, so I will include those in another video. I'll keep these pretty brief for y'all's convenience. So let's just finish the divergence and we'll move on to the others. That's going to be the next video. Let's go ahead and get that real quick from Mathematica. Okay, so this is our vector field. I did a slice vector plot in Mathematica. Again, pause the video for any of this if you want to use Mathematica. I might do a video on that as well, just raw Mathematica on how to set this up and explain all this, but so far, copy and paste, right? This is your vector field, right? It's very convenient to have this. It shows you how your heat or your flow, your work of some sort of physical concept is acting across or throughout that volume of the surface, or of the entire object that we're considering, respectively. So then now, the divergence, let's go ahead and double check all this and go through everything. Yes, indeed. And then this is our integration. Let's go ahead and do that here. So overall, we're done. That's the flux through all the entire object, right? It considers all three surfaces. We didn't have to do 3 flux integrals. That's going to be in the next video, respectfully. So hope this helps. See you in part 2. And you definitely need to do this because depending on what you have, one or the other might be more difficult, and it shows you, kind of explains what's going on a little better. So see you in the next vid. And again, this is the answer to pi for the net flux of the entire region that we're considering, the entire cylinder.